this show, Stardust, I have the total honor and privilege to work with Julie Parker, Ray, Bill Parker, John Anderson, and really Julie Parker. And Julie, John, and I got together over the last couple of years, and we've been sharing. I've always been curious about their work, and it started to conjure all kinds of questions for me. And from a number of conversations, we arrived at Stardust. And essentially, we started to interpret certain question. It's a classical question, where are we going? A number of famous artists have tried to answer it themselves. And so we decided to interpret that on 3 different scales: cosmic, human, and quantum. And so here tonight, Ray Parker, who's a quantum scientist, physicist, is going to share us about the quantum world.
Thank you. All right. Just a moment. Oh. Sorry. I got it. That's the blank one.
That was the decoy?
Yeah. Okay. Good. Okay. Thank you for coming, and thank you, Sam, for that wonderful introduction. Something's missing. Not again. There we go. All right. Good evening. I'd like to thank everybody for coming, and thank you to the artists for giving me the opportunity to speak to you. So as Sam was saying, this installation has the theme of different scales. And I'm going to be talking about what happens on the smallest scale, on the very fundamental, most fundamental scale of reality. And this is what we call quantum mechanics, is our theory of what happens at that scale. So I'd just like to start by recognizing that most people have a pretty vague idea of what quantum mechanics is. You know, maybe you've heard about something about randomness. You know, maybe the word spooky has come into it. This is kind of the fault of the way that we tend to explain quantum mechanics, right? We usually give this impression that quantum mechanics is kind of mysterious and poorly understood even by physicists. And so that can make people wonder, right? Why should we care? What's the use? Why would they give another Nobel Prize to these people, right? If you missed it, on Tuesday, they just announced that the 2025 Nobel Prize went to 3 physicists who laid the groundwork for this new revolution in quantum computing. But I'd like to say tonight that actually there's really very little that's mysterious about quantum mechanics. It's counterintuitive, but there's really only one thing that's mysterious. And I'll get to that a little bit later on. But really the reason why it's counterintuitive to us is just because we have grown up in a world where we don't see quantum effects in our daily lives. Just kind of by the way that quantum effects add up and essentially average out, we don't see all of these strange effects that I'm going to talk about. But that doesn't mean that we just give up, right? You know, it's like if you're suddenly dropped in France and you don't speak French, and everybody's going up to you speaking French, the solution is not to assume that they're all trying to speak English and try to interpret it that way, right? Like somebody comes up to you and says, bonjour, and you say, banjo? Why are people talking about banjos? It doesn't make any sense, right? The solution is to realize that the rules have changed and to try to adapt to those rules and to learn to work with them. That said, not everybody needs to know a whole lot about quantum mechanics. Right? Our civilization has lasted for 10,000 years. It lasted for 10,000 years before anybody even knew that atoms were a thing, right? And so, we don't need quantum mechanics to build canals and skyscrapers and bridges and airplanes and rocket ships. And actually, it's actively unhelpful to think about such large things on such a small scale, right? You should never drive over a bridge built by a quantum physicist, because chances are they spent more time thinking about like the movement of the electrons in the metal than they did about whether it would stand up when somebody tried to go over it. On the other hand, in the past 100 years, and actually mostly just in the last 60, our lives have in some ways become completely entwined with quantum mechanics. And this is because of all of the technology that we have developed because of our understanding of this theory. And so I believe if somehow magically all quantum effects just disappeared, right, our civilization would probably collapse overnight. That's actually not the worst thing that would happen. The worst thing that would happen is all of the atoms in the universe would collapse, and so that would be the end of everything. But the point still stands. So, while you might not need to know everything about quantum mechanics, I think everybody should have at least an appreciation of what it really is and how it's helped to shape our lives. So to begin, let's think about what is quantum mechanics, really? So I'm going to go through a number of experiments that really puzzled scientists around the beginning of the 1900s. And all of these experiments were trying to get at a question. They didn't know anything about quantum mechanics at the time because it hadn't been invented yet. The thing that they were trying to understand is, what is light? And so, to do these experiments, what we need is a light source. We need a screen that will glow when light hits it. And I'm going to add in a wall in the middle with a little hole that light can pass through. So, with these things, we can try to investigate the same way that we've been investigating for now about 400 years, what actually is light. And we're going to come to some very strange conclusions. So, to start, I'm going to have to bring up this guy that you might have heard of. His name was Isaac Newton, who was investigating light back in the 1700s. And he was doing a series of very revolutionary experiments for the time, where he would take light and he would shine it through a glass prism, and he would find that if he took sunlight, right, white light, it would break up into all these different colors. And then he could take that light and he could put it through another prism, and he could recombine them. And so he found that white light was composed of different colors of light. And his way to explain this observation was that light was made up of little particles, and that each particle had a different color. And when that particle hit your eye, you would see that color. And when a combination of those colored particles hit your eye, you would see the combination of the colors. And so let's just see what happens if we assume Isaac Newton's model for how light behaves and just see what we get if we shine this light on the wall. So if we assume that light is made of little particles, right, they all shoot out and they're blocked by the wall here, but some can pass through the hole and they end up collecting on the screen. Pretty simple. And this is about what you would expect, right? This is what you get if you take a flashlight and you shine it at a wall with a hole in it and look at what you get on the other side. And so Isaac Newton's particle theory for light perfectly explains this observation. However, at the same time, actually I should say, it looks grainy right now, but that's just because we have relatively few particles going in here. When you actually turn on a flashlight, right, there's something on the order of 10 to the 23 of these particles, if light is made of particles. And so, you would really see something more along the lines of this, bland continuum of light, right? Just kind of a bright smudge. All right. So there was another scientist at the time, Christian Huygens, who you probably haven't heard of, and he had a different theory. His theory was that light was not made of particles, but instead was made of waves. And that when you turned on your flashlight, it would be creating a disturbance in this medium, whatever it is that light exists in, and that would create ripples, just like ripples on a pond. And if it went through a constriction like this, that would kind of start the rippling over here, and you would end up with the waves traveling through. And so the picture that you get at the end is exactly the same as what you get from the particle theory. And so at the time, there was no way to tell the difference. There was no way to tell, just based on doing these experiments, whether light was made out of particles or made out of waves. And it took an embarrassingly long time to realize a better way to do these experiments. It actually took 100 years before somebody realized, wait a minute, what if we do two slits, right? So if we do two slits, let's see what happens if we now take the particle theory, right? Isaac Newton's theory. If light is made of particles, then the light will shine through, be blocked by the middle wall here, go through the two slits, and you'd get two bright splotches at the top and the bottom. That's fairly simple, right? It's just like billiards. Lots and lots of balls. All right. If, however, we take Huygens' interpretation and we think about light as waves, let's see what we get in that case. Again, these are waves just like ripples on a pond. There's nothing quantum about any of this. If you have these ripples pass through the two slits, what you find is that when the two disturbances meet up with one another, you get these regions of dark instead of light. You get patterns of light and dark, light and dark and light and dark and light and dark. Right? You get these bands. And so if you were to do this experiment and you find bands like this, then you can be fairly certain that light is not made of particles. But if you were to find instead two splotches, then you can be fairly certain that light is not made of waves. Now, I should add one little comment here about superposition. So you'll often hear the term superposition talked about as some mysterious quantum thing, but it's actually just super basic. It's what happens when you have a wave here and you add it to a wave here. what you get is the result of adding the two waves together, right? It's just, you add them up. So if I have a bright spot here and a dark spot here, sorry, if I have a bright spot here and if I have a peak here and I have a trough here, and I add them together, in the middle I'll get nothing. If I have two peaks and I add them together, I get a taller peak. Right? It's very simple. And so this principle of superposition is just a totally classical effect. It's just anything that waves do. Right? So an example I like to give is if you have a guitar string and you twang it over here, and you twang it over here, and then you twang it in both places, what you get is just what you get when you add up twanging it over here and twanging it over here. Right? It's very simple. Right. And so let's actually look at the result of what we would get if we did this experiment. I won't show you, though, what happens in between. We're going to send out some light from over here, and we're going to detect it on the screen. But just like the experiment that you can see in the back there, where we actually do this in real life, you can go up afterwards and look, we actually have a laser sending out light, going through two little slits, and you can see on the back wall the result that you get. And the result is alternating patterns of light and dark. Right? So this looks very similar to the wave picture. And so you might be led to believe, as people were for about 100 years, that light is made of waves. Right? So this experiment was first done in around 1800, and people found that light, made these patterns, and so the wave theory of light kind of won out, and that was incredibly powerful. That led to the invention of radio. That led to the invention of all of these electromagnetic effects, right? So we can use the wave theory of light, but what we found was that there were some strange inconsistencies. And it took another 100 years to realize that something is not quite right with the wave theory. And the best way to illustrate this is that people realize if you take light and you make it dimmer, right? You just make it dimmer and dimmer and dimmer and dimmer. Eventually, you start to find that it gets kind of grainy. Kind of like that particle picture that we looked at earlier. And we can make it even dimmer. We can keep going. We can decrease the amount of light that we're sending farther and farther and farther. And we start seeing more and more of these particles, fewer and fewer of these particles emerging. Until eventually, we're just left with a single particle. And so somehow, that wave pattern that we were seeing emerged from a collection of individual particles. And you might think, well, maybe they're bumping into each other and something waves. But actually what you can do is you can do this experiment where you send out a single particle of light at a time and detect just one particle of light at a time. And when you do that, what you end up with is grains. Is waves, sorry. So this this observation told us that something was very strange with the universe. You can't get something that exhibits both wave-like natures and particle-like natures with the physics that we had at the time. And so this observation really spurred the revolution that we're still living in 100 years later. Right. So yeah, how can this be? let's actually find out. So what I'm going to show you next is the result of kind of all of this pondering that people did to try to rethink how we thought we understood the universe. And the result is this theory of quantum mechanics. And I should say that we don't know that quantum mechanics is correct. In fact, we're pretty sure that there are places where it probably goes wrong. But quantum mechanics is actually our best tested theory. It's better tested than gravity. Like, we know that every time we make a prediction in quantum mechanics, it has been right. But, as we're about to see, quantum mechanics doesn't tell us everything. And so if we let this now particle of light, this particle of light evolve, what we find is that it looks like a wave, but when it reaches the detector, suddenly it becomes a particle. I don't know why it always ends up down here. It shouldn't, it's pretty random. It's just bad luck, I guess. Right, so you always get a particle at the end. If you send out a single particle of light, what you detect at the end is a single particle. But the process of that photon evolving over the course of the experiment looks like it's a wave. And so this was very puzzling. When people discovered the math that created this, now it's on the top. Yeah, it was the first one, then the second one. So when people discovered the math that produced these patterns, they had a really hard time trying to interpret what this even meant. Like, we can do the math, we can get predictions out, and when we take those predictions, we can, get the patterns that we actually see. But what actually is this thing that we're plotting here? We call it a wave function, but that's just a general term for anything that waves. And so, we have this question of like, what actually is the wave function? And for a long time, people thought, well, maybe that just is the photon. The photon is a wave function when you're not looking at it. But over time, we've come to a different intuition, that the wave function is really just a picture of the probability that we will find the particle in a particular location at a particular time. But when we look for it, we suddenly find that it is just one particle in one location, but that location is chosen completely randomly by the universe at the moment that you look at it. And this is a very puzzling notion. And actually, this is the one mystery that I mentioned at the beginning. Nobody knows why quantum mechanics does this. And in fact, we don't even know how this happens. This aspect of measuring a particle, let's do that again. This aspect of measuring a wave function, and so, wait, no, back up. This aspect of having a wave function and measuring it and finding a single particle is not part of quantum theory. It's just kind of stuck in there. It's an ad hoc thing that we've just noticed that happens. And so we can measure. Oh dear. Uh-oh. I broke it. Back up all the way. All right, there we go. So, stay. Thank you. Right. So yes, we still have this question. What actually happens when we measure? And this is a mystery. Nobody knows. We don't even know if when we don't even know when the particle is measured, right? Does the particle get measured when it hits the screen? Does it get measured when you look at it? Does it get measured when I look at it? Or maybe it's just when somebody with a PhD looks at it, right? Nobody knows. And so this is the one mystery, I think, of quantum mechanics that we're still trying to struggle with and figure out, is what actually happens when you make a measurement. Until then, the theory is perfectly cohesive, perfectly coherent. It makes perfect sense. It's just, we don't know what to do with it, right? Like, yeah. But even though we don't know, even though we can't predict where a particle will be when it's measured, and we don't know what happens when it's measured, the quantum properties of that particle are still very useful. And they have been useful in the development of the world that we live in today. So just one little example, just because it came up in the news with this Nobel Prize, I just want to show one part of quantum mechanics which is often talked about as very strange and mysterious. And that's this aspect of tunneling. And hopefully this works, because last time I didn't test that the barrier was thin enough, so we'll see if it actually makes it through. So a quantum particle, a quantum wave function, I should say, when it hits a barrier, has some probability. Oh wait, there it is. It just ended up over here. So when a quantum particle hits a barrier, you can see very slightly, there's some probability that you will end up with a wave function, you will end up finding the particle on the other side, right? Depending on the properties of that barrier, you get different amounts of the wave function passing through. And this is mysterious in the sense that if we were to measure the particle right now and ask where it is, it started on this side of the wall. It didn't have, if it were a classical particle, it didn't have enough energy to make it from this side of the wall to this side of the wall. But if we were to measure it right now and ask where is this particle, it would probably be over there because it's really bright over there. But there is a small chance that we would find it over here. And that's weird. This is impossible in classical mechanics. On the other hand, this is just what happens if you are standing in front of a window and it's bright where you are and you can kind of see your reflection in the window but also see through the window. That's tunneling. So next time you see that, you can think, hey, I'm witnessing a quantum phenomenon right now. You might win the Nobel Prize. All right, so yeah, tunneling is one part of quantum mechanics which has helped to really revolutionize our understanding of the world and our technology as well. So I called this talk, What Has Quantum Mechanics Ever Done for Us? And in case you haven't watched Monty Python's Life of Brian, there's this scene where John Cleese is talking about the Romans, and he's oh, all right, yeah. Thank you, John. Right, so aside from, maybe I'll just list them, lasers, computers, cell phones, MRI machines, right? All of these technologies. What has quantum mechanics ever done for us? Right? So, quantum mechanics has, as I said at the beginning, become completely intertwined with our everyday lives. For instance, all of you, I presume, have a little device in your pocket that's called a computer, right? You would call it a cell phone, but really it's a computer. And this is enabled by the fact that we have chips with these little switches that we call transistors, whose development was completely dependent on our understanding of quantum mechanics. There's an oft-quoted phrase from Thomas Watson, who was the CEO of IBM back in the 40s. He once said, "I think there's a world market for maybe 5 computers." Right? But now, right, there's 8 billion humans on the planet. There's more cell phones than humans. And that's just cell phones, right? If you try to count the number of computers there are, it's unthinkable, right? Every car made today has about 100 computers in it. That's just cars, right? Your fridge probably has a computer in it, maybe even your toaster, right? And so these computers and the fact that we can miniaturize them was completely driven by these quantum effects that allowed us to build transistors. And among them is tunneling. Another, that's better. Another incredible contribution to our daily lives that I think is often overlooked is the laser, right? Just that simple laser pointer, or the lasers that we're using in these projectors. The laser has really had incredible applications beyond what anybody expected them to do. For instance, DNA sequencing has been incredibly accelerated by the fact that they're using lasers. Anytime you use fiber optic internet, right? The communication is happening through lasers, or through fiber optics, but it's sent by lasers. Even, as pedestrian as going to the grocery store, right? You scan a barcode, you're using a laser. This is a quantum technology. So lasers could not exist without quantum mechanics, because a laser is this device that harnesses the resonant effects of a cavity, which is just a box for light, and atoms. So one part that I didn't have the time to get to is the fact that these quantum rules apply not just to photons, but also to things like electrons and atoms and all of these quantum particles that we often think of as normal billiard ball-like particles. And that application of quantum mechanics to these particles shows us that things like discrete energy level transitions are a thing, which means that every atom has particular energies that it responds to. And those energies correspond to different wavelengths or different colors of light. And so in the back there's an example of, actually, Dad, could you switch that on? Thank you. Of a hydrogen arc lamp, which was one of the early experiments that showed that quantum effects were there and also allowed us to measure, to validate the quantum theory extensively. And I can talk about that a little bit later if anybody has any questions about that. And one final thing that I would like, or one final technology that I would like to point out is MRI. So if you've ever had an MRI scan, the scanner has been detecting the quantum resonance of nuclei inside the protons, the quantum resonance of protons inside the nuclei inside molecules in your body. And so any time that resonance comes into it, there's a good chance that quantum mechanics comes into play. So I think I'm pretty over time, but I'd just like to make one comment on a personal level, and that's that I find another benefit of studying quantum mechanics is that it forces you to try to reconcile pictures like the ones that I showed you earlier, where if you look at light one way, it looks like a particle. And if you look at light another way, it looks like a wave. But you're always looking at the same thing. You're just looking at different sides of that thing. And so if I ever meet somebody on the street and we come into a conversation and I find that they fundamentally disagree with me about some fact that I hold dear, what I will often think is, well, maybe they're just doing an experiment where they're expecting particles, and so they find particles. And I'm doing an experiment where I'm expecting waves, so I find waves. But really, we're looking at the same thing and just trying to understand it in different ways. And so I find that thinking about things in that manner really helps to kind of look past some of the divisions that we have in the world and hopefully try to make the world a better place.
Yeah.
Thank you. Any questions in the back?
You talked about quantum events being used in computers, cell phones, et cetera. Is that tunneling, or is there, can you explain?
Yes.
What it does?
So it's a little bit, it can get a little bit in depth, but essentially when you have electrons in a material, they exist in these what are called energy bands, where they have a certain amount of energy, and they're just kind of moving around with that amount of energy. But there's this odd principle in quantum mechanics that two electrons cannot exist in the same state as one another. It's actually not that odd. It's pretty normal. It's just like this, if I take my two fingers and put them together, they don't pass through each other, right? That's actually because two electrons can't exist in the same state, right? But what that causes is in some materials, we call them insulators, all of the electrons have kind of filled up their energy levels, and they kind of create this blockade effect. So none of the electrons can move around, and they're just kind of stuck there. And that's why we call them insulators, because if I put an electrical current through it, the electrons won't flow, and so nothing happens. On the other hand, you could have a situation where you haven't filled all of these energy levels of the material, and that allows electrons to move freely because there's space for them to go up into higher energies, and they can then kind of travel around. And we call these materials conductors. There's another category of material that we call semiconductors. And these materials are kind of partway between an insulator where everything is filled up and so you can't do anything, and a conductor where you have free space. In the case of a semiconductor, you have, in most situations, filled up energy levels. But if you apply the proper biases, you can end up with electrons flowing. And our understanding of how this happens is completely quantum mechanical. So you actually need some pretty scary quantum math to really predict how these materials will work. And so these devices, semiconductors, are what we build transistors out of today. And this is what has allowed us, you can imagine, it's very powerful to have a material where in normal circumstances electricity won't flow through it. And then you apply some voltage around it, and that suddenly allows electricity to flow through it. You've just created a switch, and that can create the phone in your pocket. Any other questions?
Ray, this is sort of a two-sided question, I guess. You've been talking about very, very tiny particles, and we've not yet talked about what's inside those particles. And you can imagine that there would be things inside those particles,
yeah,
etc. And I'm wondering if there is ever a point where you get to the end and you can say, this is it. And the second part of that question is can there be any truth in science? Because at every stage of things, we're giving it our best shot, what we know as human beings, what our senses allow us to, and our brains allow us to do. And does that make any sense to you?
Yeah, no, I mean, those two questions are kind of two aspects of the same question. In the sense that this question of, are there more things as you go down, is something that people at the super colliders like CERN and all of these high energy physics experiments have been trying to figure out. And the way that they do it is by smashing things into each other and seeing how what they get out the other side compares to what the theory predicts. And for certain particles, like electrons, the theory predicts that these electrons are literally indivisible. Actually, as far as we know, there is no size of an electron. We've never been able to measure the radius of an electron. It's always, every time we make a measurement, the result that we get is always, it's smaller than some number, right? We've never found that it's, exactly this or, maybe bigger than this. It's always smaller than this. And so kind of this process of asking, what is the size of an electron, or is there anything inside an electron, is exactly coming to your second question of how do we actually arrive at truth in science? And in a sense, truth is, more or less, how hard have you tested your theory, right? How many things have you thrown at this theory to try to break it, right? And if it can't break, then you start to think, okay, maybe this thing is right. But there are certain circumstances where we know quantum mechanics doesn't work. And that's, for instance, inside black holes, right? When you try to use quantum mechanics to study black holes, the theory gives nonsense answers. It just doesn't work. And so we know that there are certain parts of the theory that are wrong. But everything else that we've tried to throw at it, every experiment we've ever done on Earth regarding quantum mechanics has told us that quantum mechanics made the right prediction. And so this is why we say that quantum mechanics is an incredibly successful theory. And we might even go so far as to call it right. But, until 1900, people called Newton's mechanics right. And so we can't say.
So I happen to have some inside information here, but I'm wondering if you could share a little bit about the images on the wall and how they're generated and what's going on in the computer in the background.
Yeah. Oh, there you go.
Is that a no?
Wait.
Schrodinger's cat.
trying to back up. Oh no, it doesn't go. All right, we gotta go. All right. So here we go. Quantum. Finally. All right. So yeah, what's going on in this simulation is we have an equation. We call it Schrodinger's equation. And this is basically the F equals ma of quantum mechanics. I don't know if any of you remember from high school physics, F equals ma is that famous law that Isaac Newton came up with that is kind of the fundamental building block of classical mechanics, right? You can send rockets to the moon and Jupiter and Pluto with F equals ma. And so what we're using here is the quantum equivalent of that equation. It's called Schrodinger's equation. What we're taking is actually the entire state of the entire room. So actually it's an incredibly computationally intensive task to do this. And that's why things like quantum computers will become a very valuable tool in the future. Because a quantum state is not just defined as, say, the location and speed of a particle, it's really the probability around the entire space that the particle could possibly be in at all times, right? And so every time step you have to take into account the entire room in your equations. And so yeah, in the back there we have a big honking GPU and all this quantum math. Although the algorithm itself is quite simple, yeah. Does that answer your question?
Kind of. Is it exactly the same every time it runs?
Yes. And well, except for the randomness, right? So all of the blobs that you see, right? All of this quantum evolution, that's exactly the same every single time. And that's because in quantum mechanics, you have this amazing reproducibility where the quantum theory tells you perfectly deterministically what's going to happen in the future if you know the current state of the system. However, when you make a measurement, that's totally random, right? So like last time I did this, it always ended up down there. I don't know why, but sometimes we get it up here. So yeah, that's, is that? Yeah. I saw one back here.
Yes, one. I do have another question if you want to pick up something else.
Okay, go ahead.
So if you were explaining this to a bunch of fifth graders,
Yeah.
assuming that they have less of the capacity of understanding this than we do, which may not be the case, what words would you use to tell them what's happening on the walls?
Well, I mean, we could talk about the weather, right? So, for instance, when you read the weather report, or the weather prediction for tomorrow, right? They tell you there's a 70% chance that it will rain, I hope, because we need the rain. That prediction, has a lot of statistics behind it. But when you the way that you actually make the measurement is by experiencing tomorrow, right? So you wait until tomorrow. Did it rain? No, probably, just based on the streak that we've had. And so what we're seeing here is kind of everywhere it's bright, right? You're seeing there's a high probability that you would find a particle there when you make the measurement. And so this wall is kind of like the weather prediction for making a particle measurement. That, when we make the measurement, this is telling us, it's trying to predict not the future, not in a deterministic sense, but in a sense of, where are you, if you did this experiment many, many times, what would you end up with? It is, however, very powerful in the sense that it can tell you that you're very unlikely to find the particle down here, right? Where it's dark. Well, I guess it's not dark there anymore. You can kind of turn the problem on its head and say, all right, I'm probably not going to find the particle, anywhere. I guess. I think Sam and then.
Yeah. So can you go back to all that activity you had there?
Yeah.
Right, so you have a barrier here, right?
Hang on.
So there's a change here. What's going on here from this side of the barrier to this one? What's that?
Yeah,
what's
so
happening?
this is actually, you really can think of this exactly like you're looking at a shop window, right? So you're standing outside a shop, it's a sunny day, and you're looking in the window, and you see your reflection.
Yeah.
But you also see what's going on inside the shop,
Yeah.
right? The wave function started here, right? So the light started over here, and it went towards the
Glass
window,
Yeah.
and some part of it got reflected, and some part of it went through.
Okay.
And so, what we have here is kind of this semi-permeable barrier where, you might find the particle, or where, I should say, the wave function can traverse that barrier. And the result is that if you look for the particle, there's a good chance that you'll find it over here,
But
even
in a
though
more diminished,
well,
because,
it's less likely,
okay.
right? So it's less likely to find it over here, but it's always the particle. It's always one particle, and it's always got the same amount of stuff in it. It's always the same mass, same energy. Everything about the particle is the same when you find it, right? It's just you find it over here more often than you would find it over here.
And it doesn't matter what material that barrier is, whether it's glass or concrete or...
Well, it does. So the material of the barrier changes the properties of it, makes it either more transparent or less transparent to the particle. So the first time I did this, it wasn't transparent enough, and so it just bounced right off. And I was like, oh, it was a block of concrete when I wanted a window.
Right.
Yeah.
Just abstract the scope of tonight's topic, I guess, but in quantum physics we hear about its relationship to other dimensions, and multiple dimensions, perhaps infinite dimensions, and shown in science fiction movies. Is that something you can comment on?
So when you say dimensions, like that term is kind of, there's many definitions.
Non-physical dimensions,
But do you mean like different universes or different possibilities, or just like different directions that aren't 3D?
I mean, it could be other physical dimensions, but in metaphysics they talk about the astral plane and the causal plane.
Yeah.
They're not physical dimensions that are multiples of the physical plane that we know, or even just multiple galaxies. You're standing there in this dimension, but in the next dimension you're over in this side.
Right.
I don't know what I'm asking.
No, it's a good. So yeah, there's many different directions you can take a question like that, depending on what we're talking about. So, for instance, if you're talking about different realities, right? Different possibilities of reality, then there actually is an interpretation of quantum mechanics, right? Kind of this question of what happens when you make a measurement, right? This one mystery that we still don't understand. There is an interpretation of quantum mechanics where when I make a measurement, say I find the particle over here, right? In some other reality, an equally valid reality, I measured it over here. And all of these realities exist simultaneously. It's just that as soon as the measurement is made, you can't interact from one reality to the other. And so this is a very hotly debated possibility in quantum mechanics, but nothing has ever ruled it out. So it could be totally valid. Then this question of different dimensions, say spatial dimensions. That is another question that people have in just kind of physics in general, is how many dimensions are there in the world? And for instance, string theory makes this prediction that like you could solve all problems in physics if only space has 11 dimensions, and 11 minus 3, whatever that is, are just very, very well hidden, and we've just never seen them. So yeah, these are very interesting questions with a lot of different directions you can take them. Yeah, maybe last question.
Do you still talk about wave functions collapsing when you take a measurement?
Yeah, so that's kind of the most standard interpretation of quantum mechanics. Standard as in kind of the one that they teach in textbooks and classes, where when you have a wave function, right, it's spread out over this entire space. Right? It's what we call a non-local thing, right? It doesn't exist in any one location. And then when you make the measurement, all of that possibility suddenly collapses down into one point, right? And so yeah, that is kind of the most standard interpretation of quantum mechanics, is that happens immediately at the point of measurement, and don't think too hard about it. There are a number of philosophical problems with that idea, but again, like the many worlds interpretation, for now it's just a philosophical debate, because there right now isn't an experiment that could tell the difference. Yeah. All right, so I think I've kept you guys much longer than expected. So. Cool.
Thank you, guys.
Thank you
Thank you.
so much, you guys, for coming.